All right, so get ready because today we're taking a deep dive into something truly mind-blowing, how cells actually live. And trust me, it's way more dynamic than just picturing a bunch of molecules like just hanging out. We're diving deep into energy, causality, and the living cell. The Schrödinger Machine concept.
Yeah, it's a fascinating paper.
You sent this in. It really grabbed my attention. So we're tackling the age-old question, what is life?
Right.
But we're looking at it from the perspective of how cells avoid decay. And it even hints at the Schrödinger machine idea, which color me intrigued.
You know, what I find really captivating about this paper is that it doesn't just give us a parts list for a cell, like some kind of boring inventory.
Mm-hmm.
It digs into how these parts are constantly in motion,
Rebuilding.
recycling. And ultimately, that's what makes life, well, alive, right?
It's like comparing a cell membrane to a bustling city, right?
Exactly.
And the paper even makes that analogy because it's constantly under construction. Things are always changing. It's not just this static wall, which honestly, I always kind of pictured it as before this.
Yeah. The paper really emphasizes that this constant renewal is all about actively fighting against reaching a state of equilibrium.
Okay, so break that down for me. Why is equilibrium like the enemy for a living cell?
Well, just imagine for a second a cell where everything is perfectly balanced.
Mm-hmm.
Nothing really changes. I mean, it sounds peaceful, maybe, but
Right.
It actually means no more growth, no adaptation, no response to the environment. Essentially, it's a cell that's just given up on living.
Wow, so it's like cells are constantly outrunning death by staying in motion.
Yeah.
And this dynamics outlet the paper talks about, is that connected to this whole idea?
Precisely. The paper suggests that this constant turnover of material within cells, all this, building up and breaking down, it might actually be crucial for maintaining a state of disequilibrium, that essential imbalance that defines life.
So it's not just about what a cell is made of, but how it's constantly changing and using energy to never stand still.
Yes.
That's a pretty radical way of looking at it.
It is. And it gets even more interesting when we start to think about how cells actually generate and utilize that energy, which brings us to the rock star of cellular energy, ATP.
So cells are working overtime, right? Fighting equilibrium just to stay alive. But that kind of energy expenditure, it's got to take a serious fuel source.
Right.
Which brings us to ATP, the rock star of cellular energy. But I got to admit, I always kind of pictured ATP like tiny little batteries. Each one's got these high energy bonds just waiting to be unleashed.
Yeah. It's a super common misconception, that whole high energy bond thing. Even textbooks mess it up sometimes.
Yeah.
The really cool part is that, yes, ATP hydrolysis releases energy.
Yeah.
But what's really key is how the cell balances things out between ATP and ADP. It's delicate.
So less like individual batteries and more like, I don't know, what's a good analogy? Like a giant hydroelectric dam, maybe? Constant flow, difference in potential energy, that kind.
Oh, that's good. That's a fantastic analogy.
Yeah.
And the paper really hits on this point, that it's the cell's ability to keep ATP levels way higher than ADP. That's what creates the driving force for all those metabolic reactions we're talking about. It's like a battery that's constantly recharging, always maintaining that energy gradient.
And that brings us to this crazy fact from the paper that we, as humans, synthesize our body weight in ATP every single day.
Every day.
That's an insane amount of activity every second without us even knowing what that even look like, practically speaking.
It really just shows how efficient these cellular machines are. Think about
Yeah.
everything your body does. Breathing, thinking, moving. It's all powered by this constant back and forth of ATP being made and broken down.
Mind-boggling, really. And we haven't even touched on another big piece of this puzzle that the paper brings up, which is thermal energy.
Right.
It's easy to forget that heat isn't just a byproduct, but actually crucial to how life works at the most basic level.
Absolutely. The paper makes a really strong case for thermal energy, especially how it affects molecular motion.
Yeah.
I mean, without it, all those carefully orchestrated cellular processes we've been talking about, they'd just grind to a halt.
Wait, so you're saying that even the random, jiggling of molecules is essential for life? Help me wrap my head around that one.
It all comes down to how that jiggling, that inherent thermal energy, it's what lets proteins fold correctly. And it allows for this super intricate dance of molecular recognition. And those processes, they're the foundation for pretty much everything a cell does.
So it's not even just about the molecules themselves. It's the fact that they're constantly jiggling around, right?
Yeah.
That's what lets them interact and do their thing.
Yeah.
And the paper keeps mentioning this conformational space. Sounds kind of like I don't know, where molecules go to unwind after a long day. What does that actually mean?
Uh-huh. Well, it's a little more complicated than a vacation spot, but the idea of exploring is right on. Picture this, a huge landscape. You've got mountains, you've got valleys, but instead of like actual geography, they represent the different energy states a molecule can have.
Okay.
So thermal energy, it's like a free pass for these molecules to move around this landscape, try out all kinds of shapes. That's conformational space.
So instead of these rigid little structures, we're talking about more like, I don't know, flexible dancers, trying out different moves until they find the perfect fit for whatever reaction needs to happen.
Precisely. Like a lock and key, you know? Sometimes it takes a little wiggling to get everything lined up just right. And that wiggling, that's often coming from this constant exploration of conformational space, all thanks to thermal energy. Without it, so many essential interactions in a cell just, they wouldn't happen.
Okay, so let me see if I'm putting this all together now. We've got ATP, that's our driving force. Then we've got thermal energy, getting the party started. And on top of that, you have all these processes we've talked about, like this constant renewal, making sure the party never actually stops.
It's a beautifully orchestrated cellular rave, really.
Haha, I like it.
And it brings us to the big idea the paper keeps hinting at, the Schrödinger machine.
Right. We've been dancing around it long enough. What is a Schrödinger machine exactly, in the context of a living cell, I mean?
It's a bold idea. They're saying cells aren't just machines as a metaphor, but in a real physical sense. They've evolved to use thermal energy, that random jiggling, to power all the reactions needed for life.
So instead of being driven by some outside force, they're actually tapping into this energy that's already there all around them and constantly pulling themselves further and further away from equilibrium in the process.
Exactly. They're like incredibly efficient little heat engines using thermal energy to stay in that crucial state of disequilibrium that we keep coming back to.
Wow. So we've gone from cells as like simple bags of molecules to bustling cities to now these intricate self-winding machines.
It's a pretty amazing leap, isn't it?
It really is. But it makes you think, too. If a single cell can be this Schrödinger machine harnessing chaos to make order, what other incredible possibilities are out there, just hidden within life itself? And that's it for today's deep dive. Huge thanks to you for joining us and for sending in this incredible paper. It's given us a lot to think about. Until next time.